In the last class we were discussing about the associative memory and just the introductory part of it, and today we are going to continue with the detailed discussion on associative memories, and in particular we will be taking the associative memory model, both from the structural aspect as well as from the mathematical point of view. Now, yesterday we were listing out some of the characteristics of the associative memory, and one of that I think you must have noted. That's to say that the associative memory is highly distributed in nature. So it's a distributed memory system. It's not confined to one place. Okay, it is distributed, and that is of course motivated from the biological neuron consideration. So let us look at some modeling that one can make about the associative memories realized out of biological neurons. Okay, let us take certain number of neurons. Let's say that we take M neurons, okay, which are interconnected in an associative memory way. Okay, so what we will be having in that case is that, let us first consider the input layer. So we will be having from the input, okay, several neurons, okay, which will be connected to the neurons at the output layer. So here we will be having the input layer, and here we will be having the output layer. Okay, and in between these two we will be having the synaptic connections. Okay, so all the synaptic junctions will be existing like this. That supposing we indicate the synaptic junction in this manner. Okay, like this. Okay, so these are, all these things are nothing but the synaptic junctions. So how is the association or the memory storage actually taking place? We are feeding the patterns at the input layer, okay, and we are obtaining the response from the output layer. So whatever is stored, okay, is actually stored in the form of the synaptic weights. Okay, now this is one area of the memory, okay, which is responsible for the storage of information. Okay, and there what is being done is that we will be having a set of synaptic weights. Okay, but this set of synaptic weights will act in such a way that if you are feeding any specific pattern, let's say that you were feeding a specific pattern xk in the form of a vector. By vector I mean to say considering all these elements, okay, considering all these m elements. Let's say that there are m elements at the input and there are m elements at the output. It's not mandatory that the input number of neurons and the output neurons, they have to be same in number. They could be different, but without any loss of generality one can consider it this way, that we have the same numbers at the input and output. Perhaps just to ease out our analysis part, but in fact the analysis can be carried out for even different number of inputs at the input and the a different number of neurons at the input and the output layers. So what happens is that this memory or this synaptic junctions will be responsible for the storage of patterns, in the sense that if we are feeding any input pattern, okay, let's say that a particular pattern xk in the form of a vector that we feed, in that case we should get the corresponding yk vector which is supposed to be the output, and if we get that, then one can say that there is an association between the input xk and the output yk, okay, both in the form of vectors. Okay, so that means to say that we are essentially looking for the association between the xk vector and the yk vector, where xk is the input and yk is the output. So So in effect what it is doing is that it is as if to say memorizing the xk yk pair, but not explicitly. What it does is that in the form of this synaptic weights, so that when xk is fed over here you get yk. Okay. Similarly, when x1 is fed here you get y1. Okay. So whatever pattern you feed, okay, you can recall that pattern. Okay. By feeding that pattern as a stimulus, you can recall that pattern, recall its response from the output. Okay. So that's what it is. So this is from the biological model point of view. Okay. And whenever we consider the ANN model, it is almost the same, but only that the representation is slightly different. So there too also we can consider, okay, as an example again the case of M neurons. Okay. And let us say that we consider any pattern, any particular pattern K. Okay. So here by this K I mean to say the index of the pattern. So x1, x2, x3 and all these things will mean the first pattern, second pattern, third pattern, like that, and these are all in the form of vectors. Okay. So let us take the kth pattern. Okay. And we will be having xk1 as the first input, let us say. Okay. Then we will be having xk2 as the second input, and likewise we will be having xkm as the mth input. Okay. So these are available at the input layer. So likewise we will be having an input layer for the ANN model also. So this is the ANN model of associative memory. Okay. And these will be connected to the neurons, okay, or you can say the output neurons, which will do the processing part. Processing means what kind of a processing? In this case it is fairly simple, that take any neuron, let us say that we take the neuron that generates the output y1, or in this case we will write yk1, because for the pattern k, okay, the response that we are getting from the neuron, output neuron indexed as 1. So yk1 will mean the output from neuron indexed as 1 for the pattern k, right. So we will be having yk1, yk2, etc. up to ykm, just because in this particular case we had considered the number of input neurons and the number of output neurons to be the same, and as I told you that they could be different also. Okay. Now what happens is that every neuron will be having the connections from the other inputs. So this will be connected to xk1, xk2 and up to xkm. Likewise yk2 will be connected to xk1, xk2 up to xkm, and likewise ykm, continuing this way, ykm will be connected to xk1, xk2 up to xkm. Okay. This is the ANN model. So it is essentially the same only, and this case what happens is that we will be designating each of these connections, okay, by their synaptic weights. So in this case what we have to consider is that if we are taking a particular pattern k, okay, and we are considering this connection, let us say this connection means what, that it is a connection that is there between 1 and 1, okay, output 1 and the input 1. So we will be writing it as W11, but just to indicate the pattern number also, what we do is that within parenthesis we give a pattern number. So we will be calling this synaptic connection by W11K. What we will be calling this connection, that is xk2 to yk1, W12K. Okay. So like this connection from xkm to xk1 we will be calling as W1MK, right. And now going over to the second output neuron, that is output neuron number 2, we will be having the synaptic connection as, from between this x1 and the y2, the synaptic connection will be W21. Again within bracket we have to write K. So the very purpose that we are writing K is that these weights, at least we know that these weights have been designed so that for the pattern K, okay, these weights are suited to this pattern K, so that when the input Xk is applied, you get the output as Yk. But there lies a question, does this network have only, memory for only one pattern? Certainly not. We are going to store a large number of patterns within this memory, okay. But then why is it that we are writing it as W1K? Because the moment we write anything with a bracket or suffix or superscript, whatever, with K, that means to say that it is only for the kth pattern that I am considering. Okay, for the time being we consider one pattern, or rather the kth pattern only, but in effect when we design the total combination of these weights, when we design this set of weights, that time we have to consider the effects of all the pattern. So that means to say that the final weights that we will be having will be from the combined contributions of all the patterns, okay. This I am writing as K just to indicate that for the association of Xk with Yk, this will be the synaptic weights, W11K, W12K, like that up to W1Mk, again W21K, W22K, up to W2Mk, finally up to Wm1K, Wm2K, up to Wmmk. Alright. Now, let us, in these lines we can easily formulate, okay, the mathematical part of it, okay. I think the representation now is going to be pretty simple, okay. Let us see that what is going to be our definition of the vectors as such. Now, we started with two vectors, the input stimulus, which we called as the Xk vector, and the output, corresponding output, okay, which is associated with this input, is Yk vector. So what is this Xk and Yk? So Xk vectors definition is essentially, it is Xk1, Xk2, etc. up to Xkm, okay. And we will be having the, in fact we can write this as, it is customary to write this as transpose, meaning that by vector we will be meaning the column vector. So likewise Yk vector will be defined as Yk1, Yk2, etc. up to Ykm, okay, again the transpose of this, okay. And okay, so now we consider the response for any one of the neurons, okay. Let us say that we consider the response of, these are the outputs Yk1, Yk2 up to Ykm. So we consider the response of the jth neuron in the output layer for the pattern K again. So we are considering Ykg, alright. So what can be the representation of Ykj? Here Ykj we could represent as, okay, as summation of W what J, and then again some other index we have to say. So we can say Wji for the pattern K, and here we have to write Xk what? Xki, okay, and we have to sum it up over I is equal to 1 to m. So what is the index I? The index I in this case is for the inputs, okay. So I is equal to 1, I is equal to 2 up to I is equal to m. These are the input numbers. So these are all the Xki's, okay, and then these are the Wgi's are the corresponding weights between the output neuron J and the input neuron K, and the input neuron I, okay, for the pattern K, and we are adding it up, this from over I is equal to 1 to m, right. So this is what we are getting for Yki, okay, and this in the matrix form, okay, we can translate like this. So the same Ykj we can now write as Ykj equal to W, what are we going to write here? Wj1, right? Wj1k, Wj2k, etc., up to Wjmk. Okay, these being the weight vector. Okay, so weights are also written in the form of a vector, and this will be multiplied by what? This will be multiplied by xk1, xk2, etc., up to xkm. So this is the matrix representation of the same equation that we had described earlier. Okay, so if we call this as equation number 1, okay, in that case equation number 2 is nothing but a matrix representation of equation number 1 only. Okay, and mind you that this equation will be valid for j is equal to 1, 2, etc., up to m. Alright. So if this is valid for j is equal to 1, 2, up to m, in that case it is possible for us to write down m such equations. We can write yk1 is equal to, in this case we will be having w11, w12 up to w1m, yk2 will be equal to w21, w22, etc., up to this. So we can write m such equations, and if we write m such equations, okay, and take all the left hand sides of it, so all the left hand sides will now indicate yk1, yk2, yk3, etc., up to ykm. So if all these outputs we take together and represent the outputs in the form of a vector, then what do I get? Then I will be getting the vector of the output y as follows. So we will be having the y vector represented as yk1, yk2 up to ykm, alright, and that will be equal to something. Okay, we have to see that what is that, but essentially all these individual inputs will be equal to, will be a function of all these xk1s, isn't it? In every equation this part will be common, am I right? This vector, it has to be, the individual weight vector, this weight vectors will be different, because for the case of j is equal to 1, it will be w11, w12 up to w1m. For j is equal to 2, it will be w21, 22 up to 2m, like that. Okay, so this will change. Okay, with every j it changes, but this remains the same. So essentially, since this is going to change, then for every such j's we are going to have a different weight vector, but in effect that means to say that it will give rise to a weight matrix. Okay, so we are going to write it down as w11k, w12k up to w1mk, okay, as the first row of this, and in the x vector we will be having xk1, xk2 up to xkm. So as you can see that yk1 is going to be equal to w11 xk1, w12 xk2 up to w1m xkm. Okay, so all these will be added. So this is what we want, isn't it? So this really verifies the equation. So whatever we had, if you put j is equal to 1, you can get yk1 from the multiplication of this with this, alright, and likewise yk2 you will be getting as w12k, w22k up to w2mk. That's very correct, yes, you have pointed out a mistake. It should be w21k, because all the time our notation is that whenever we are writing the weight, it should be first the output index, in this case 2, and then the input index, in this case 1. So it is 2, 1, 2, 2 up to 2m, and this will be wm1k Wm2k, the last line, the last row will be Wm2k up to the last element will be Wmmk. So this is the full matrix representation which gives us effectively the relationship between yk vector, this is nothing but the yk vector, right, and this is nothing but the xk vector. So this relationship gives us the representation, or rather the associations between the pattern xk and yk. So this is giving this association. Okay. Now this is not the only pattern, we are going to have many such patterns. Let us say that we have got patterns which can be indicated by k1, 2, etc., etc. up to q. Alright. So we will be having lot of such patterns, but okay, now let us look at this matrix equation, okay, that we have got. Okay. So how we can represent it? We can simply represent it as yk vector will be equal to what? Wk. In this case Wk will be a matrix, this particular matrix that we have got. So this matrix Wk times what? The xk vector. Okay, so it is Wk and xk vectors product which will be yk. So what we are going to have is that y1 vector will be equal to w1 vector, x1 vector, like that, as if to say that with every pattern we are going to have a different set of weights, as if to say that for every pattern it has to memorize a different set of weights, but that is not the case. In fact, what happens is that, I mean, as we keep on feeding the patterns, okay, now for every pattern it learns, okay, it associates this yk with xk, that means to say that it forms wk, but then it keeps on adding to its existing weight. So initially we can say that we begin with the weight as w0, okay, could be that all the synaptic connections they are initialized to 0, and we then feed the first pattern, get w1, okay, feed the second pattern, we get w2, and then whenever we are getting the second pattern we are adding w1 with w2. When we feed the third pattern we are adding w1, w2 and w3. So what we are putting into the memory, okay, is memory also is going to be in the form of a matrix now, isn't it? All these W matrix elements will go into the memory, but in the memory what we will be actually storing is the summation of weight matrices. So in the memory we will be storing like the M matrix will be equal to summation of all the W matrix, okay, WKs, but for k is equal to 1 to q, okay, assuming that there are q such patterns, okay. So that means to say that what is this, so this is what this M matrix is an M by M memory matrix. So M by M memory matrix's definition is this, that it indicates a summation of weight matrices, okay. Now in effect that means to say that this M matrix basically indicates to us the total experience that is gained out of q different patterns, okay. So M indicates the total experience gained. Now how do we gain experience? We feed patterns one by one, okay, and we formulate their weight matrix, and we add that weight matrix to the M matrix, okay, to the existing M matrix. In fact, this equation, okay, which we can now write it as equation number 4, equation number 4 can be written in the form of a recursive relation. So equation 4 can be rewritten in a recursive form, okay, and what is it that we can write? We can write that the M vector, I mean the M matrix, okay, after feeding the kth pattern. Okay, now kth pattern means we are assuming that we are feeding the pattern from 1, 2, etc., etc. in sequence. So 1, 2 up to q we are feeding. So we are feeding the kth pattern. Now after feeding the kth pattern, the memory matrix composition will be the memory matrix composition which we had at the end of k minus 1 patterns, okay, plus the weight wk that we have gained from the experience. Again, I mean kth patterns experience gives us the weight wk which we add to this mk minus 1, that is the previous experience that we had gained plus the present experience that we are getting is our new experience, which is m of k. So this is in the form of a recursive relation. So that means to say that if we write it in this recursive form, in that case I mean the two boundary conditions that we have to note is that m0, that means to say that before feeding any pattern we are assuming that the memory was 0, that means to say we did not have any experience to begin with, and finally, I mean since we are assuming q number of patterns, I mean the experience that we gain after feeding the qth pattern will be nothing but the M matrix. I mean given that the M matrix definition is this summation from k is equal to 1 to q of this wk. Okay. So these are the boundary condition. Now what you are doing is that you are adding this wk to mk1. Okay. Now the question is that can you really I mean retain the identity of this wk in this mk matrix? You are only adding to it, and if there are large number of such patterns, okay, and if you are adding one by one, it is as if to say like adding droplets to the ocean. Okay, I mean you have already got a large collection of patterns and you are only adding the experience of the new pattern to it. So it is an incremental addition, but again this incremental addition is necessary. Why? Because ultimately this M matrix indicates our total experience gained. Okay, this M matrix will now indicate the set of synaptic weights. So again, if we are taking the associative memory model as we had done in the beginning, so when it goes through all the Q patterns, then we will be having a matrix M, okay, indicating the total synaptic interconnection over here, which will be such that you feed a pattern xk next time, okay, you should get the pattern yk retrieved from that. I mean it should have an exact retrieval of patterns. Okay. Now whether we can do the exact retrieval or our retrieval is prone to some errors, okay, that is something that we have to see. Again, one can also ask another question at this point that well and fine, we are feeding such kind of patterns, okay, individual patterns we are feeding with k is equal to 1, 2, etc., etc., okay. Now okay, can we guarantee the exact retrieval aspect? I mean that's what I think I was trying to talk to, and we will be coming to that. Okay. So let us see, I mean this particular equation that we have written in a recursive form, okay, let us remember that, okay, yeah, I mean I just now remembered what I was trying to say over here. Well and fine, I mean we know, I mean we have already said that this M matrix is going to be the total experience gain. So that means to say that we are as if to say computing the weights, okay. But how do we compute the weights? On what basis? On what basis are we computing the weights in order to reaching this figure? Okay, we haven't formulated any learning rules, or not that it is as per the arbitrary weights, that we did not define any updating equation. So that means to say that, as if to say that we have to somehow estimate that weights in some manner, okay, and then once again when we estimate the memory matrix, that means to say in that case, instead of M matrix, we are going to have M cap matrix as the estimated matrix. So again it depends that how good our estimates are. Our estimates may be good, our estimates may not be all that good. So how do we estimate that? Okay. So this has given rise to a concept of what is called by the correlation matrix memory. Okay. So that is what we are going to discuss now. All right. Now, yes, please. Any question?
What is matrix M cylinders?
Yes.
Matrix M is the sum of all the weights depending on the input which we had till now.
Yes.
Now, how does it associate with it with a particular input is given, that which set of weights is to be pulled down? Like 2 plus 2 is equal to 4, 2 plus 3 is equal to 5. I should have been storing that difference of 1, output is so much. What I have done is, I have added up everything.
Okay. Let me repeat the question, because the audience mic may not be all the time audible. So let me repeat the question. The question which was asked to me just now is that we are formulating the memory matrix, okay, as a summation of the individual weights. Now the question was that what is the guarantee that when we feed the kth pattern as a stimulus, okay, we will be retrieving the kth component of the weight, okay, because the kth component of the weight is no longer there, it has all got mixed up into the memory matrix M only. So this was the question. In fact, just to clarify your doubts, similar doubts which others also may be having, we are not retrieving the weights. Please don't make this mistake. What we have to do is that, given that memory matrix M, okay, now the WK component is lost. We have got the updated memory matrix M. Now the question is that, given the memory matrix M, is it possible for us that if we feed the input pattern X of K to it, okay, can we retrieve the output pattern YK exactly? If the given matrix M permits us to do that, our job is done, because we are only noting the association between YK and XK. We are not bothered about whether we could really identify the WK component or not. Okay. You are adding a spoon of sugar to water. Okay. Now you are ultimately interested in testing sweet water. Okay. You don't want that what is the exact sugar that you have put into it. Okay, something of that. I don't know whether this analogy is too simplified or not. So is that understood? Anybody having any similar doubts to it?
So that means when we have XK and YK,
Yes.
and YK equals WK times XK.
Yes.
And then we also saying that YK equals MK times XK.
Yes. So what happens is that, yes, YK is equal to, yes, YK we are saying to be equal to WK XK, and then we are adding this WK to the memory matrix, and then we are also saying, yes, that YK is equal to MXK. Okay, we are saying that. That means to say that this M is containing all the W's. Okay, so this M is the total experience of learning. So now, yes, indeed, that's what is going to happen, that we are now going to retrieve the pattern out of this combined memory matrix M, forgetting about what we had as W's. Very right. Okay, so we can discuss about the correlation matrix memory, and in this case we have to see that how do we estimate this memory matrix M. Okay. So, we come up with an estimate of the memory matrix, and estimate we are writing as M cap. So, M cap is the estimated memory matrix, okay, again indicating it with the vector notation because it is the matrix, okay, and we just make a postulate. So, this is a kind of postulate that we are presenting over here, that this M matrix could be considered as a summation of k is equal to 1 to q yk vector times xk transpose vector, okay, and summation of this. Okay, let us come to the interpretation of this. Now, what was our problem? What I said was that we are not knowing any explicit weight, so we are going to estimate these weights wk's. But now we are saying that we are going to estimate this total matrix. We are going to come forward with an estimate of this matrix M, which we are calling as M cap. Now, what is this expression? This is definitely a vector multiplication. And what form of product is this? Is it an inner product or is it an outer product? Outer product. You see, this one yk vector is what? This yk vector is an m by 1 vector, okay. So, this is yk, which is m by 1 vector, and then we are considering xk transpose vector, and what is that? That is 1 by m vector, okay, and we are taking the outer product of these two, okay, and summing it up for all the patterns k is equal to 1 to q. So, when you do the product of an m by 1 vector with 1 by m vector, what do you get? You get m by m matrix, okay. So, this is the matrix that you will be getting out of this, and you are summing up all the matrices. Well and fine, because what you actually have is the input stimulus and the output response. You are having only this. So, essentially you have stored the response in response to a stimulus. So, you take the outer product of that and you store it into the memory. So, this memory M will ultimately contain the summation of all the outer products of this pattern association, okay. Now, this equation, okay, can be now, I mean, this is a summation of all these outer product vectors, okay, and we can reformulate this equation as follows. Now, what was our last numbering of the equation? Remember? That was 4, okay. In fact, this recursive relation we can make as number 5, so that now we can number it to be equation number 6. Now, I can reformulate the equation 6 in this way. So, equation 6 may be reformulated as m cap, okay, again we have to take the m cap as the matrix ultimately, and writing this way yk xk transpose inevitably means that we could indicate it by the combination of vectors, okay. So, we can, I mean, since it is going to be a summation for k is equal to 1 to q, what we can write is that we can write the individual vectors, that is y1 vector, y2 vector up to yq vector, again because we have got q patterns fed to the system, okay, and the input stimuli corresponding to that are x1 transpose vector, x2 transpose vector up to xq transpose vector, okay. This we are going to represent in the form of a column vector, I mean arranging all these vectors into again another column vector. So, this in effect can be written as y vector, where y vector is actually whose each elements are all these individual pattern vectors. Is it understood? So, the elements of this capital Y vector is all these individual pattern vectors, okay, times we are going to write again, we are again going to define another vector which will be the capital X vector, and capital X vector will be containing the elements as x1 vector, x2 vector, like that. So, effectively we are going to have the x transpose vector, okay. So, y vector times x transpose vector, in this case the inner product of these two vectors is going to give us the memory. In fact, since essentially the product of this y1 and x1 transpose, they are going to give us the m by m memory matrix, they are going to give us m by m matrix. Essentially it will mean to say that the dimensionality of this m cap is going to be of the order m by m. So, here I think I have already told, but just to note down that the definition of x vector is that it is x1 vector, x2 vector up to xk vector, and y vector will be nothing but y1 vector, y2 vector, etc. up to yk vector. YQ, thank you very much. Yes, this is YQ because we are going to have Q patterns. K is only an index which will vary from K is equal to 1 to Q. Thank you for this correction. Now, again this expression, okay, that we have got, that M cap matrix is equal to Y vector matrix times X transpose vector, okay. This could be restructured again in the recursive form. How? We can write it in a recursive way as m corresponding to the iteration k. That means to say that after feeding the kth pattern, okay, we should write it as mk cap matrix will be equal to mk minus 1 cap matrix, okay, plus yk pattern. So, you have fed the kth pattern. So, this was the earlier experience gain, and you have now fed the kth pattern, and you are taking the outer products of the response and the stimulus, okay, and this you are going to have for k is equal to 1 to up to q. So, this is nothing but a recursive form of equation 7. So, if I take it to be equation 7, this or this whatever, okay, this is nothing but the recursive form of 7 is going to be this. So, we can call it as the recursive relation, we can call it as equation number 8, and just we can depict it pictorially as follows, that we can feed as an input to this system the yk vector coming from here, again from the other input we are getting the xk. In fact, yeah, I mean I should have told it like this. See, here xk is the stimulus for the kth pattern, and the corresponding association or the corresponding output is yk. So, we are trying to memorize this yk, okay. So, how? That we have got an association of xk and yk already. So, we are taking the product of these two, and then what we are doing, we are taking the outer product and we are accumulating that into the M array. In what manner? We are going to have, let us say that this is the M cap matrix that we have got, okay. This we can put through a unit delay, so which we can write as z to the power minus 1, indicating an unit delay, and multiplying it by the identity matrix I, okay, and this we will be getting from the output as mk minus 1 cap vector, okay. The because this is one delay letter. So, if this is mk, then this is going to be mk minus 1, okay, the earlier. So, what we are doing is that this mk minus 1 we are adding to the present pattern. So, this is what we have already gained, and we are adding it to the present association of yk and xk, and we are updating the memory matrix as mk. Alright. So, this is just a pictorial representation of this. Okay. Anybody having any doubts? Yes, please.
So we need yk to get, we need mk to
Yes.
get yk, and we are needing yk to estimate mk.
We are getting, see, effectively what it means is that you have got an association of yk with xk, and you are taking the outer product of that association and you are storing it into your memory. I mean you are incrementally adding that to your memory. Okay. Now, once that memory is there, okay, the updated memory that you have got, which is in fact indicating the sum total of all the experience that is gained. Okay. Now, what you are having is that you will later on, once you have a memory matrix M already available with you, then you can feed a stimulus. Okay, let us say that you again repeat a stimulus xj, okay, from this set of patterns which you have already gone through. Now, if your learning is proper, okay, then it should give, in response to this xj, if you can retrieve the pattern yk, yj exactly, in that case that is what we are wanting, isn't it? Okay, that later on any pattern association that we are making, we can get it back. So, the estimate of mk is coming from xk and yk, you are very correct. Okay, and then ultimately what we are doing is that when we want to retrieve any pattern, we will be feeding an xk and we will be seeing that if out of that we get the yk or not. In effect, that means to say that if we get, if we feed a pattern, let us say that we have already formulated the memory matrix M. Okay, so this is M cap, our estimated memory matrix, and we have fed a pattern xj. After learning, after we have already stored. So this is a total, this is the last iteration that we have gone through. So we have gone through all the Q patterns, and now in order to test this system, I just happen to pick up the jth pattern out of it, okay, and I feed the jth pattern as an input. So my output, corresponding output, will be again a vector, which will be y vector, which will be equal to M cap matrix times xj vector. Now, what I should ideally have is that if y vector is equal to what? Yj vector, okay, if y vector is equal to yj vector, then I can say that the recall is perfect. Is that understood? Okay, all of you agreed? So that's what we would like to investigate now, that whether our recall, okay, is going to be perfect or not. So we are going to study the recall aspect. Okay. Now let us see that if it is so or not, okay, and if not, then what is the condition that we have to fulfill for perfect association. This is what we are going to investigate. So we don't know yet that if this is going to be true. So that's why I have just put a general vector y. Okay, I did not intentionally designate it by y1 or y2 or yj. I expect yj, but I did not intentionally put yj because I don't know yet that whether I will get the exact yj or not. Now let us expand this. Basically what we can write in place of the M vector, M matrix is this expression. This was our definition, isn't it? It is either you follow this, or yeah, I mean a better expression is this. So this is the expression of the M cap matrix, okay, which is the summation of all the outer products for k is equal to 1 to q. And now what we are going to do is that in this expression we are going to replace this M cap vector by this expression, M cap matrix by this outer product expression. So if we put in that case we can write down the y vector as summation over k is equal to 1 to let us say that we have got m different patterns. So this we can have as y is equal to that yeah, yk vector times xk transpose vector, okay, and xj, okay. This xj remains the same. So this xj I am keeping as undisturbed, and only in place of this m cap I have just put forward this. Now you can see over here that I did not put the limit as k is equal to 1 to q, instead I have put the limit as k is equal to 1 to m, okay. And what is m? You remember that as per our original definition, okay, this was our associative memory model, okay. So we had m inputs and we had got m outputs, so that we can say that this network is having an m dimensionality, and we have somehow restricted the total learning within its dimensionality. That means to say that if there are 100 neurons in this associative memory model, we are saying that we are not going to teach this more than 100 patterns, okay. We can then see that whether our assumption is correct. If it is capable of learning more, we will teach him more, okay, but if it is not, okay, then we have to restrict. So that is why, just to make a restriction, I say that okay, if there are m inputs, I am not going to teach you more than m, okay, at least should be less equal. So I mean we can just teach up to m patterns only. And now what we can do is that this summation that we have got, it is very much possible for us to rewrite this product expression, and I can say k is equal to 1 to m, and I can now associate xk transpose xj transpose, okay, now xk transpose xj. So I associate this and then I multiply it by yk. I can do that, okay, I can do that, and this now I expand. This is for k is equal to 1 to m. Now very interestingly, when I am summing it up for k is equal to 1 to m, one of the indices that it has to pass through in this summation is when k is equal to j, and when k is equal to j, then very interestingly this term becomes xj transpose xj, okay, times yj, okay, and then other than j there will be all other m minus 1 terms. So what I do is that this summation that we have got, we are simply separating it out between the jth term and the non-j terms summation. So we can write it as y vector, this could be represented as xj transpose xj, okay, yj. So taking the jth term out and then keeping the summation as it is from k is equal to 1 to m, only restriction is that not for k equal to j. So it is for k not equal to j that we sum up. The rest of the terms keeping as it is xk transpose xj, okay, yk, okay, these terms remain as it is. Now what is it? What is this term? Can you interpret this? This is the, yes, this is the magnitude of the jth pattern, okay, the squared magnitude of the jth pattern. Okay. And what is that? In effect, it is the energy. Now, we can say that if each of the patterns x1, x2, etc., up to xm, if all these patterns are normalized to have unit energy. So, if this is having unit energy, then what is the energy expression? The kth vector, let us say, the kth vector's energy, kth x vector's energy will be summation of x kl square, okay, and L summed up from 1 to m. Okay. In this case, this is going to be xk transpose xk. Okay. So, if this is equal to 1, that means to say what? That in this expression we substitute xj transpose xj to be equal to 1, and in that case what do we get? You get y is equal to yj plus this term. Now, you expected y to be equal to yj, and there is one additional term which is coming in between, which is creating the trouble for us. This additional term that we are getting is essentially a noisy term. So, in the next class we will see that how to deal with this noisy term. Thank you very much.